Hello and welcome to today's webinar. This is a virtual masterclass on the lessons learned from the 2024 Worldwide External Quality Assessment Scheme for molecular testing of BRCA and other homologous recombination repair gene variants in ovarian and prostate cancer. So I'm joined today by Dr. Simon Patton, who's my colleague from EMQN, and I'm Professor Sandy Deans, Director of GenQA. And together we are both EQA providers deliver these assessments. So next slide, please. So just some housekeeping slides for you and some information. So just to avoid any background noise so you can hear the presentations, your microphone will automatically be muted. And we have recording this webinar so we can then provide it through the GenQA and the EMQN YouTube channels for you to watch again at a later date. We would be really keen for you to submit some questions in the Q&A function that you can see hopefully on your screen. And if you do that, we'll be able to address them at the end of the webinar slide deck. And Simon and myself hopefully will be able to give you some feedback and answer those questions. Next slide, please. So be able to provide feedback and provide you with webinars that you really want to hear about some of the work that we do. Your feedback is really important to us. So to be able to continue to provide high quality training to you as healthcare professionals, we would like to hear from you. So you'll receive an email after the masterclass with a link just to provide some short feedback on the survey. So we ask really just to take a couple of minutes to be able to do that, and we'll be able to respond and deliver the webinars that fit your needs. Next slide, please. So I'm now going to hand over to Simon, my co-chair and presenter today, to kick us off with the webinar. Thank you, Simon.
Thank you very much indeed, Sandy, for the introduction and the housekeeping. Next slide, please. So this is our disclaimer. Next slide, please. So just a couple of slides really just to get us into the mood and the flavour of what we've been doing. So this, as Sandy alluded to, is a collaboration between EMQN and GenQA, two established EQA providers in the field of genomics. And what we're going to be talking about today is a summary, if you like, of the results and findings from the 2024 version of these EQAs, which cover germline and somatic testing germline and somatic BRCA testing in ovarian cancer and somatic HRR testing in prostate cancer. So we've been running these schemes for quite a few years, particularly the germline and somatic for 9 years, and for the prostate cancer scheme, the ctDNA, this is the third year that we've run this scheme. We're very grateful to the support from MSD and AstraZeneca for an educational grant, which allows us to be able to provide these EQAs to the labs at a subsidised cost. And just the structure of how we deliver them hasn't really changed over those years, but effectively the process is providing 3 samples, EQA samples, for each sub-scheme, distributed with a mock clinical case. And this includes, the referral information as well as the sample itself that's distributed. And then we ask all laboratories to make sure that they test that sample with their routine protocols and report back their results to us, the EQA providers, with the results of their analytical processes and the interpretation they would have given on the analytical result. Now, these activities are very time-consuming to deliver, but we can't really deliver them without the support of our peer group of assessors. And this year, we've had 31 colleagues from around the world, from 12 different countries, have helped to actually deliver these EQA schemes. Each of those EQA schemes has been marked against a harmonised set of marking criteria to ensure consistency both within the schemes and between the schemes. And you can see on the graph on the right-hand side, the charts here say that we have quite a broad, diverse group of individuals from around the world who've actually helped us deliver these EQA schemes for the different sub-schemes, broken out by the different colours. Next slide, please. So just a simple, if you like, understanding of what the EQA actually does and how it actually works. So the primary principles behind most EQA schemes, in genetics anyway, is that we provide the same material for testing for all the laboratories that take part. The laboratories return the results back to us as the assessment coordinating body for our overview and review of their results. We do ask every laboratory taking part to treat the samples in the same way you would as a patient sample. So that's utilizing your routine procedures and personnel who perform the test. Interesting fact that not everybody treats it the same way as a patient sample, but nevertheless, that's the expectation from the laboratory side of things. And then we assess the results against the predetermined marking criteria to understand the accuracy of each laboratory test and how it's been reported. Now, the advantage of this type of approach that's provided from an external provider is it's an external measure of the quality of the service of a laboratory. But most importantly, I think here, we're not just about sort of the regulatory side of things, we'll come on to that in a second, but as EQA provides, we put a lot of effort into trying to help improve laboratory performance through education and training. But undeniably, there is still a performance perspective that comes into the regulatory framework. So regulators and commissioners of services do take note of the EQA performances, and in some cases, some jurisdictions can actually suspend laboratory testing if they're persistently performing poorly. Everyone can make a single instance of mistakes, but it's the laboratories that make repeated mistakes, the ones where the regulators will take most note. And for all these three schemes, we're now in a phase where they are all full EQA schemes. There's no pilot schemes associated with them. So performance monitoring was applied to each one of the sub-schemes. Next slide, please. So I'm going to run through the results of the germline testing scheme, the sub-scheme on BRCA and HRR genes in ovarian, breast, prostate, and pancreatic cancer. Next slide, please. So just a quick overview of the demographics of the participants in this year's scheme. So you can see that we've had a bit of a drop this year in 2024 in terms of the total number of laboratories that participated. Primarily, I think, driven by the fact that there was now a fee applied to participating in the EQA scheme, albeit a small fee. But you can see when you look at the breakdown of laboratories, new versus existing laboratories, still about a quarter of laboratories are new to the EQA scheme. So we're still attracting every year new laboratories that haven't previously participated in this activity. And then when you break down the geographical region that the laboratories are participating from, you can see that the biggest trend here over the last 3 years is that the number of laboratories participating from the EU has increased, and there's been a drop-off in laboratories participating from the Asia-Pacific region and China specifically. Next slide, please. So for the germline schemes, the samples that we sent to the laboratories were 3 genomic DNA samples. These were extracted from cell lines, EMQN cell lines, lymphoblastoid cell lines. We selected them based on known variants. And as is common for all of our EQA schemes, these samples don't go out to the laboratories until they've been independently validated by at least 2 different laboratories prior to distribution. We're talking quite a lot, and I think you'll see a theme in the discussions today about CMV analysis, but we wanted to highlight the fact that CMV analysis is now a standard practice, certainly in the germline setting. So all of our samples are validated for CMV detection or CMV analysis before they go out to the laboratories. So you can see that the 2 laboratories that we used this year were both using NGS strategies. And both of those strategies included a CMV analysis component of the validation process. And in one case, well, in fact, both cases, there was independent validation of any confirmed pathogenic variants using an orthogonal technique just to make sure that we were happy with the variants detected. So in this case, in both laboratories used Sanger sequencing for the orthogonal component of the validation process. Next slide, please. So let's dig a bit more detail into each individual case. Don't forget there were 3 cases. So case 1 this year was a lady who had been referred for breast cancer. So ER2, HER2 negative breast cancer that had metastasized, and she was being considered for PARP inhibitor therapy. So germline testing had been requested. So the question we were asking here, is there a pathogenic variant present in the germline sample? Next slide, please. So looking at the expected result, so this was a case where we expected laboratories to detect a heterozygous duplication of BRCA1, exon 12. Now, the exon of interest was either exon 12 if you use systematic exon numbering, or if you'd use legacy numbering, then actually the duplication would have come up as a duplication of exon 13. So a very strong component of this was just assessing how the laboratories had called it and what nomenclature they'd used to call the exon, because it did differ depending on which one you'd used. We were not expecting to find any pathogenic variants in BRCA2. Looking at the analytical reporting, so the genotyping of the test results, 65% of laboratories correctly genotyped that sample, with a further just under 20% of laboratories correctly genotyping it within the limitations of the test they'd used. So this was obviously a CNV test. We were expecting laboratories to report the duplication. So those 20% of laboratories probably didn't test for CNVs, but did at least report that as a limitation of their test. However, there were just over 15% of laboratories that had a critical genotyping error. And when you break down those results themselves, you can see that the majority, well, there's a large number of laboratories made false negative errors, so failure to report the heterozygous duplication, and then a number of false positive results as well associated with detection of a deletion instead of a duplication, or reporting variants in BRCA2 rather than BRCA1, including potentially a CMV in BRCA2, or in one case, laboratory reporting duplications of exons 12 and 13, and finally, one laboratory detecting a different variant in BRCA2. Next slide, please. 1 second while I just move my speaker slide. So looking just a little bit more detail at the types of problem made. CMV testing should be considered routine for germline testing, but we did find a lot of problems with the laboratories able to detect duplication in BRCA1. False negative results included failure to report the deletion, despite actually saying they'd undertaken CNV analysis, failure to clearly describe whether copy number variants were detected by the method used in the report, or when they weren't performing CNV analysis, not actually referring the sample on for further CNV testing, maybe by a second or a different laboratory. There were also quite a number of laboratories making mistakes associated with how they actually numbered the exon duplication. This partly depends on how they actually named what nomenclature they're actually using, as described in the results expected. But also, this duplication itself extended outside of the transcript. And strictly, if you were really applying the nomenclature rules, you'd require a genomic reference sequence to provide that to describe exactly where the breakpoint of the duplication was. There was variability considerable variability in the nomenclature used to report that duplication as a consequence. Next slide, please. Looking at the interpretive component of the result as well now, there were 3 critical interpretation errors this year. All 3 were in laboratories that described the variant as a variant of uncertain significance, VUS, and then none of them made any further recommendations for further analysis. A large number of laboratories didn't test for CNV analysis, and with some failing to recommend further testing for large genomic rearrangements. And we included this sample because obviously in the context of germline testing, LGRs, and particularly copy number variants, can account for up to 15% of all inherited BRCA1 and BRCA2 variants. And therefore, it's clinically relevant to perform this type of testing. So we really want to understand and reinforce the educational component that CNV analysis in the context of BRCA1 and BRCA2 testing is absolutely essential, and particularly in the germline setting. It was unclear in many reports whether CNV analysis had been performed. So again, laboratories lost marks if they didn't clearly state the scopes and limitations of their tests. and whether further testing should be recommended if it wasn't performed in-house. Next slide, please. So case 2 was a lady who had been diagnosed with serous ovarian cancer, and her tumour had been shown to be sensitive to platinum-based therapy. Testing was required to inform treatment decisions using PARP inhibitors. And again, in this case, like all the cases, we're asking, is a pathogenic variant present in her germline DNA? Next slide, please. So in this case, there was no expected pathogenic variants in BRCA1, but we were looking for the laboratories to detect a heterozygous BRCA2 variant, splice-like variant in one of the in an intronic region. So the analytical component of the results was pretty good in this case. So 99% of laboratories correctly got the results correct, with 2 laboratories reporting false negative results for the BRCA2 variant. Next slide, please. There were no critical interpretation errors, which is great to see. If laboratories did lose marks, they were predominantly for not actually defining the prediction of the biological impact of the splice-like variant that was present in BRCA2. So as a rule of thumb, when intronic variants are described in relation to a DNA coding sequence reference, the nature of the splice site should include that genomic reference. The other common reason for deductions was failure to state the implications of the result, the analytical result, the genotyping on family members. Quite a few laboratories lost marks for that. And some laboratories didn't mention that the patient themselves may be at risk of developing other BRCA-related cancers. Next slide, please. Case 3 was a man who had castration-resistant prostate cancer that had metastasized to his bones. He had had hormone treatment, and chemotherapy was now being considered for PARP inhibitors. And tumor testing for BRCA variants had failed due to inadequate tissue. So in this case, again, this is a metastatic setting for prostate cancer, and we're looking for is a pathogenic variant present in the germline DNA of this individual. Next slide, please. Looking at the analytical results, so we weren't expecting any pathogenic variants in either BRCA1 or BRCA2, and nearly all the laboratories got the result completely correct. So this obviously is an example where we would probably expect to see false positive results, and there were 3 false positive results from laboratories, accounting for just over 1% of all the tests undertaken, where an unspecified BRCA variant had been detected. Next slide, please. There were no critical interpretation errors, and really the only systematic problems we detected, and for which there were common deductions, if you like, was failure to provide a statement on PARP inhibitor therapy, so the relevance of that treatment, and failure to recommend that a cfDNA sample or a repeat tumor sample should be tested. There were no deductions given in this case, as the referral stated that previous tumor tissue had been tested. Next slide, please. What strikes you when you look at the results of this scheme is just how many different methodological approaches are used for the same clinical scenario. So there were just over 220 laboratories taking part, and 203 different approaches used by those 200 plus laboratories. So it's a really broad number of different tests being used to answer this question, the questions associated with the 3 cases. Not going to go into detail, but it's a real theme of these EQAs that there's just the sheer number of different tests that are being used by the testing community undertaking these strategies. Next slide, please. Looking at the results, so we use a deductive marking scheme. So if a laboratory scores maximum, there's a maximum of 2 points, and any mistakes or errors will lead to deductions from 2. In laboratories that can get completely the wrong results, so the critical genotyping or interpretation error would get 0 points for that category. So looking at the genotyping scores, don't forget case 1 was a CNV case, and we expected to see a lower score for genotyping and interpretation, and that is reflected in the results. Whereas cases 2 and 3 were much more consistently analysed, and you saw from the results, pretty good results all round for both genotyping and interpretation. So the scores, the genotyping and interpretation scores, reflect the fact that those cases were done more successfully than case one. Next slide, please. Looking at the performance trends over time, graph on the left-hand side shows you the percentage of participation, and in the blue bars is the number of laboratories that submitted results. The purple bars, those that didn't submit results and didn't tell the EQA providers, and finally, in grey, the laboratories that withdrew but did at least notify the EQA providers that they were going to withdraw. And you can see that the number of laboratories withdrawing this kind of fluctuates a bit around about the 5%. And across the board, the number of laboratories that don't submit results, either through withdrawal or just no given reason, is about 10 or 11% in this year's scheme, which has seen a consistent improvement over time. So it has in the past been nearly 20%. And when you look at the results this year, the results of the genotyping interpretation are kind of predicated on how difficult or easy the case scenarios that we make for these samples are. So you do expect to see some fluctuation. But you can see that generally the scores for both genotyping and interpretation are pretty consistent, certainly generally above 1.6, which indicates laboratories are doing a pretty good job of the interpretation and the genotyping. Looking at the critical error rates, you can see that from this year, that the critical error rate for genotyping was nearly 7%, which is quite high. And over the last 9 years or so, we provided four samples that have contained CMV analysis. And consistently, those samples are showing pretty high levels of genotyping errors, indicating that those type of samples are more challenging. And therefore, we would expect to see elevations of the error rates as associated in those years when we've included a CMV. The interpretation critical error rate was about 0.5%, I think it was this year. And you can see over the last 3 years, that's been certainly less than 1%, which is good to see. We don't normally see huge numbers of critical interpretation errors, but the analytical component is significantly more variable. Looking at the poor performing laboratories, a poor performing laboratory is any laboratory that makes a critical error would be classified as a poor performer. But some laboratories make critical errors in more than one case, and that's what's reflected in the graph at the bottom. So the number of poor performing laboratories across the EQA this year was about 16%, so considerably higher than it has been in previous years. And given the fact there was a smaller number of laboratories participating as well, that's been taken into account in the percentage. And you can see that the majority of errors that caused poor performance relate to only one case, but there are a couple of cases where laboratories have made critical errors in two of the 3 cases, and in one case where a laboratory made critical errors in all 3 cases. So these latter laboratories, the ones that make 2 and 3, would be classified as persistent poor performance, and then obviously they would be followed up as a consequence of that to ensure that they were undertaking the right root cause analysis to understand why the errors were caused. So overall, I think the data is showing that it's strongly suggesting that CMV analysis is difficult, but should, as we discussed previously, be incorporated into the laboratory testing strategy. The number of poor performers has increased, but again, this is reflected by the challenging nature of the cases we provided certainly over the last 2 years, where we're really starting to challenge the laboratory's testing strategies to make sure that they are delivering on what should be considered routine practice within the germline testing BRCA. Next slide, please. So I'm now going to hand over to my colleague Sandy Deans for the somatic BRCA testing.
Thank you, Simon. That was very nice to see the germline findings. So next slide, please. So in parallel to the germline EQA, we also provide somatic testing, which reflects the practice that happens in our genomic testing pathway. So again, as with the germline, we can actually look at the demographics of our participating laboratories. We, as always, see a very good uptake in the somatic EQA, and that has remained around the 350 participating laboratories who sign up and register to participate. You can also see that we have new laboratories joining every year, which does mean that the existing previous participating labs are dropping out. So I think the message here really is, if you participate in EQA, you should be doing that annually, and that we would like to see repeat participation from laboratories, because you're only as good as your last EQA run, and that really don't want it to stretch out longer than 12 months. We also see a slight change in the number of participants from Europe. Across Europe, we see a slight increase from previous years, and a very small decrease in those laboratories from Asia Pacific geographies across the globe. But all in all, you can definitely say it's a global participation in this EQA, covering all of the continents. So next slide, please. So for the somatic EQA, I think the challenges of how we deliver the EQA is different from the germline, and we've got different types of ways of testing. So we have to make sure the EQA is fit for purpose for somatic testing. So first of all, we need to assess the ability of laboratories to extract high quality DNA from tissue samples. So we provide FFPE material, as extraction is really important as part of that process. So it's not just about the genotyping testing or the reporting, it's about that upstream sample handling as well. Now, we know we can't provide EQA true patient material for the number of the participants, which is, as I said, up at 350. So we have to start looking at different ways of delivering that FFPE material that mimics the real true patient sample. We also have a range of laboratories testing and different testing strategies, and we have to be mindful that there are differences in different regions and different nations. So we want to make sure the EQA is fit for purpose for all of our participants. But we do expect both BRCA1 and BRCA2 to be tested. And we deliver, obviously, the germline and somatic testing with a range of different clinical scenarios, which take into account that some laboratories will test the tumour first, and some may test the germline first. So we need to make sure it's agnostic for all approaches. We also have to have variable experience interpreting the variants. With our variant interpretation EQAs, we do see a challenge of that activity. So we like to provide a range of the types of variants and across different classifications, just to see how many laboratories are reporting different types of variant classifications and whether that's appropriate or not. And we do have expert review of the classification evidence when that has been submitted. One of the key points of the somatic EQA is also understanding the importance of the potential germline variants. So just because it's a tissue test or mimicking a tissue test doesn't necessarily mean it is a somatic variant that is being detected. So we do include the consideration of germline variants in our marking criteria, and we discuss this more in depth with the EQA summary report and the webinar that we're holding today. Next slide, please. So the design of the EQA is, again, we're looking at the ability of the participant laboratories to correctly determine the genotype of the FFPE tissue samples we provide, interpret those results in response and in context to the clinical referral, obviously in a clear, concise format, so the result cannot be misinterpreted in any way. We will be looking for correct use of internationally accepted standard nomenclature, and provide appropriate and accurate patient and sample information and identifiers. We surprisingly still see clerical errors with incorrect patient identifiers, for example, in the EQA reports that are submitted. And for the first time this year, we've introduced our fourth case in the EQA run. And this is to start addressing the somatic testing for large genomic regions. And as Simon's just very eloquently pointed out about the challenges of CMV testing in the germline setting, well, then we know that this is also very challenging in the somatic testing. And we also started to introduce not just BRCA1, BRCA2 testing, but also testing for other HRR genes. So next slide, please. So our EQA samples, as I say, we have to be mindful that they represent real patient material without the ability to use patient material. So we have constructed 3 artificial FFPE cell line samples manufactured by Horizon Discovery using the EMQN cell lines. And these cell lines were selected for the specific variants that they incorporated. So after the sectioning, so that we generate the cell lines, they're embedded in the paraffin, and then they're sectioned, and then all samples are independently validated by 3 laboratories before distribution. And to mimic really what's happening on the ground, that this independent validation is performed by NGS. And really that's just to make sure that, one, after the shipping, that labs can obtain a reportable result, and also that the expected genotype in the samples is as we expect. So here you can see we've got 3 different testing strategies to be used per each laboratory. One's through the QIAGEN NGS on a NovaSeq. One is an exome sequencing also on the NovaSeq using the enriched twist exome library prep, and the third is a customized setup NGS panel. So we're covering all the boxes for our participants. Next slide, please. So we start with case 1. Our scenario is a gentleman with castration-resistant prostate cancer that has metastasized. So he's had hormone treatment and is now being tested to determine eligibility for PARP inhibitors. So that is our referral, is a metastatic cancer referral following first-line treatment. So we want to know, is there a pathogenic variant present in his tumor that can be detected from these samples? Next slide, please. So the genotyping result for this case was there were no pathogenic variants detected in BRCA1, but there was a stop variant in BRCA2 detected. Now we had 3.5% of our participating laboratories reported the incorrect genotype. So this is 12 critical genotyping errors. So if this was a true patient, you would actually have 12 patients, 12 laboratories would have reported the incorrect result. So the majority of incorrect answers were actually false negatives. So there was no detection of that BRCA variant. So that's 7 laboratories. We had the incorrect variant reported. So within the report, there were discordant, I should say, variants reported in the same report, which meant that the reader of the report really would not know which variant was actually present in the sample. So 2 laboratories came across this error. We had 2 further laboratories with false positive results. So one had reported the presence of a different BRCA2 variant, and the other had reported 2 deletions within BRCA1. And then, which we often see, one laboratory had submitted results incorrectly to this case. It was actually looked like the results from the case 2. So at some point in their processing, whether it's at sample reception, extraction, assessing, actual testing, or reporting, they've actually switched the cases round. Next slide, please. The good news is our critical interpretation error rate was very low, with only 1 participant actually gaining a critical error in this category, and that was the incorrectly stated that truncating variants are poor therapeutic targets. So this laboratory received feedback from our expert advisors. Next slide, please. So moving on to case 2, this was a ovarian cancer referral. So this lady had been diagnosed with serous ovarian cancer. Again, she had received platinum-based chemotherapy, which her tumour had not responded to. And she was now being considered for maintenance treatment with PARP inhibitors. So again, we were requesting the minimum of BRCA1, BRCA2 testing, and is there a pathogenic variant present in her tumour sample? Next slide, please. So the expected validated results for this lady's tumour was that there was a splice site variant in BRCA1 and no pathogenic variants detected in BRCA2. Now we had 20 critical genotyping errors, so more than we had previously seen, which was hovering just under the 6% of participants. Again, the majority of these laboratories had reported a false negative result. So they failed to report the presence of this BRCA1 variant, and that was 10 of them. So half of the participants had a false negative result. We also had a range of different BRCA variants reported, and 3 laboratories came up with very, very different variants detected, and also 2 laboratories provided incorrect variant numbering for the reference sequence provided. So in actual fact, reading the report, you would not have been able to identify the location of the variant according to the reference sequence they provided. We had 2 further laboratories with different false positive results, one again in BRCA1 and another in BRCA2. And then, as previously described and detected in case 1, we had 1 laboratory who appeared to have switched the results for case 1 and case 2, and then we had a further 2 laboratories that actually had switched it with case 4. Next slide, please. The good news is we had no critical interpretation errors, which is fantastic to hear. So there were some deductions, but no critical patient affecting interpretation errors. What we did observe was many laboratories did not actually provide a biological impact of that splice variant detected. And really, when intronic variants are described in relation to a coding DNA reference, the nomenclature for the splice variant should include a genomic reference as well, and that contains the uninterrupted genomic DNA sequence, which does include your introns, because your code and DNA reference sequence do not contain the intronic sequences. So it's really important that you have that genomic reference on your report. Next slide, please. So now moving on to case 3. This was one of the cases that we provided for testing of more than just BRCA1 and BRCA2. We wanted to start looking at the assessment and the quality of testing of other HRR genes. So this individual had, again, castration-resistant prostate cancer, and it had metastasized to his bones. So again, he had had hormone treatment and chemotherapy and was being considered for treatment with the PARP inhibitors. So here you can see we had a full range of testing requested, and laboratories were asked to provide the testing that they routinely use. So they were not expected to set up any extra testing for participation in this EQA, but we wanted to look further than just BRCA2 and BRCA1 and BRCA2 testing. So we wanted to know a detection of HRR gene pathogenic variants. Next slide, please. So the validated results were that for this list of the genes that are on the top of this slide, no pathogenic variants were detected. However, there was a pathogenic variant detected in the gene ATM, according to this reference sequence. So we took a slightly different approach when we were assessing this case, because we did not know that all laboratories were testing all of the genes. So when we were assessing, we had to take into account the scope of the testing that the laboratory stated that they were performing, so what was listed in the report. So if ATM gene testing wasn't performed and a result of no pathogenic variants was detected, then that was accepted as correct, because it was correct within the limitation of the testing being performed. But to note, over 50%, so 54% of our participants did perform ATM testing. So that's 189 laboratories. So it's good to see that we either had a correct result because the ATM testing wasn't performed, but they didn't detect variants in the other genes tested, or the ATM variant was detected. So next slide, please. What we did find was we had 8 critical genotyping errors, not the same as the other cases whereby it was predominantly false negative results being reported. This case achieved more false positive results. So we had a BRCA2 variant detected, a PAL-B variant detected, as 2 variants detected, a BRCA1 variant detected by one laboratory. We had 1 laboratory detected variants in BRCA1, BRCA2, and PALB2 as pathogenic. We had a laboratory with multiple variants in BRCA1 and BRCA2, and then we had 3 laboratories failing to detect the ATM variant, but it clearly stated on the report that the ATM gene was included in their assay and had been tested. Next slide, please. Again, though, as we saw with case 2, we had no critical interpretation errors. So the observations from the EQA report submitted for this case, approval of PARP inhibitors for the treatment of patients with prostate cancer with ATM variant is very heterogeneous. It depends the region or the country that the testing is being performed. So the content of the report did vary considerably depending on national or local approaches. We were looking for participants to comment on PARP inhibitors in relation to the clinical referral provided and to comment on referring this patient to clinical genetics, because there was an opportunity that ATM variant actually would be germline. So it's critical that that referral or suggestion or recommendation should be included on the report. Next slide, please. So very interestingly, the data that we have gathered from our educational case. So as I mentioned, for the first time, we have added a 4th case in. This lady had platinum sensitive serous ovarian cancer as part of the clinical referral. So she's had surgery, received a round of platinum-based chemotherapy, and is being considered for maintenance PARP inhibitor therapy. So we requested BRCA1 and BRCA2 testing, and also it was mandatory to test for LGRs, deletions and insertions over 25 base pairs, up to whole gene deletions and duplications. So this was mandatory for this case. So the rationale, not really looking at the interpretation in particular detail here, it was to assess the ability to accurately detect the LRGs. Next slide, please. So the validated results for this case were no pathogenic variants or LRGs in BRCA2, but here we did have an LRG in BRCA1, and according to this reference gene, it was exon 7 deletion, so a whole exon deletion. So here you can see a breakdown in the pie chart. Approximately half of the laboratories did not test LRGs and half did. And of those that did test, we had a genotyping error rate of around 19%. So that was 32 laboratories reported the incorrect result. So the breakdown of that is 22 of them failed to report exon 7 deletion. So that was a false negative result. We had 7 reporting false positive results, and then we had the 2 laboratories that I previously described who had switched the results from case 3 and case 4. So next slide, please. So a breakdown of the results that were falsely reported. These are our false positives. Again, you can see no trend, that there was no low levels of any other variants present. We have a raft of either an actual SNV or exon 14 deletion or exon 20 or exon 17, or a duplication that's a VUS in BRCA2. We also had a laboratory reporting a BRCA1 rearrangement and a BRCA2 deletion. So really no trend or any indication that there was something wrong with the sample there. Next slide, please. We had 3 critical gene interpretation errors. So 2 laboratories reported a recognized benign BRCA2 variant that we know was present in the sample, but they reported it as a variant of clinical significance, so received a critical interpretation error. And 1 laboratory identified the exon 7 deletion, but stated incorrectly that PARP inhibitors were not clinically relevant for the patient, so provided the incorrect clinical interpretation. Next slide, please. So just the observations here that we can all learn from. So some laboratory returned the results, but they didn't perform the testing for the LRGs, and it was really mandatory for this case for assessment that that was tested and reported. So we did not mark these laboratories for this case. Many laboratories did not explicitly state on the report whether or not they offered CNV testing or admitted it from the limitations of the reports. But were not detected as pathogenic CNV was reported. We did not require HGVS nomenclature to describe the copy number variants, but where HGVS was used, it was assessed against the current guidelines from HGVS. So we were not prescriptive about using HGVS as long as there was a clear written statement of that result. And many laboratories reported the BRCA exon deletion as exon 8 rather than exon 7, but they did not state the custom or legacy exon numbering was used. So they provided the incorrect gene reference sequence for the exon numbering. So a half a mark point deduction was applied if incorrect exon numbering was stated for that transcript provided without mentioning which numbering system they had used for exons. Next slide, please. So overall comments from the somatic scheme are potential germline variants, as we keep saying. About 54 to 73% of BRCA1, BRCA2 pathogenics in ovarian cancer are inherited. So it is really good practice to refer patients to clinical genetics for further investigation of the potential impact that it may be a pathogenic variant. So it should not be assumed that it is a somatic variant. But still, some laboratories did not comment on this in their reports. And recommendations, if the referral reason is that the patients are being considered for treatment with PARP inhibitors, then we're expecting some mention of this, the relevance of the result in that context on the report. And we saw several laboratories continually failing to describe a recommendation use of PARP inhibitors. Next slide, please. As Simon described, there are multiple different methodologies and testing strategies in play here for somatic, just as we've seen with the germline, and many different approaches as insufficient detail of what is being tested and the limitations of the test on the EQA, on the laboratory reports. So we really would like to see the scope of the testing is covered, and whether or not it's all coding sequences, for example, and the limit of detection of their assays must be included, because that is pertinent, particularly if you're reporting a no pathogenic variant result. Next slide, please. So here you can see very significantly and very obviously a drop in the quality of the genotyping in case 4 when we were looking for those that exon deletion, and subsequently also a drop in the quality of interpretation. Now, we can't assume that's because of the incorrect genotype, because if a laboratory receives an incorrect genotype, then they are not marked for interpretation. So this is a further subset of laboratories who are not interpreting the presence of that exon deletion correctly. But you can see with the other 3 cases that we are genuinely getting a high quality of test, and also throwing in the ATM variant in case 3 has not had a detrimental impact on the quality of genotyping or interpretation. Next slide, please. And just looking at the performance and the participation trends here, you can see from this year we're seeing fewer labs withdrawing, which is fantastic to see. So we always like those that register to actually participate, but we still had quite a large number of laboratories who did not submit results. Looking at the trend data, particularly the critical error rates, you can see really considerable increase in the genotyping error here with our CNV detection there, and also the percentage of performing laboratories poorly in that educational case and across the EQA. So a very high quality standard for cases, case 1 and case 2. Case 1 was more challenging, and then of course you can see case 4. But the case 4 was educational, so we don't apply any performance monitoring on that case. It was purely educational. So we would recommend, if you did receive deductions for that case in particular, that you do review your processes. Thank you. That would be helpful. Okay, next slide, please. So Simon, I'm going to come to you for a slightly different slant now on somatic testing, and that's looking at cell-free DNA testing.
Thank you very much indeed, Sandy. So next slide, please. So in our somatic, so our ctDNA testing scheme, obviously this has been only running for 3 years, and the first 2 years are actually pilot schemes. So this year was the first year when we applied performance metrics for this scheme. And you can see that converse to the other 2 schemes, the germline and the somatic, actually the majority of the laboratories participating in this scheme are new to the EQA. And as Sandy said before, the the existing laboratories are as crucial to this test process. We'd like to see more laboratories participating on a regular basis, so that we have less new laboratories and it's consistently new existing laboratories participating. The evidence is very strongly in favour of the fact that consistent participation definitely improves performance over time. Looking at the breakdown of the demographics, where the laboratories come from, again, very similar to the other two schemes. It's a global EQA scheme. Obviously, the numbers are lower, and the numbers of laboratories in Europe has increased slightly. We've seen an increase also in laboratories from China, and a slight drop-off in laboratories from the Asia-Pacific region. But overall, it's still a global EQA scheme with representation from all the regions in the world. Next slide, please. The challenge of this scheme is very similar, obviously, to the somatic scheme, but there are some unique challenges for cfDNA, and one of those is just getting samples that you can actually use in a cfDNA format. I'm sure many of you are familiar with the challenge of finding reference materials to actually use for cfDNA testing. And that challenge is amplified in the context of EQA when you're wanting to provide the same sample to all the laboratories participating. cfDNA EQA is difficult to deliver, and obtaining high quality cfDNA samples is absolutely essential to making it work. So we provide a cfDNA plasma matrix that tried to replicate real true plasma, but was nevertheless stable in the terms of context of shipping. We have a global number of laboratories. We want to be sure that that sample is going to work in all the regions of the world. And so the materials we use have been validated to make sure that they are stable at a broad range of ambient temperatures. But we do also track the failure rates associated with that, just to make sure that the samples that are reaching the laboratories are stable. Understanding the limitations of cfDNA testing is also very important for us as well. So complicated or difficult NGS tests, due to primarily to this type of sample type or test context and variant allele frequency. We also find a large number of laboratories are using inappropriate test strategies. So strategies that have been built up based on their experience from FFPE don't necessarily translate to the cfDNA setting. So that's one of the things we take into account in our assessment process. And obviously variable experience in interpreting variants. So again, this is a common theme across all of the schemes. And when we try to incorporate into our EQAs a broad range of different types of variants and different classifications to make sure that laboratories are able to interpret those correctly in the context of the samples that have been sent as well. And like Sandy was talking about in the somatic scheme, we have expert review of our classification evidence to ensure that we are actually interpreting those variants correctly before we assess the laboratories against it. And as Sandy said in the previous slide, understanding the importance of potential germline variants is also key to this type of testing. So we include in our marking criteria that cover this area. And then those points are discussed in our EQA summary report and in this webinar as well. Next slide, please. So we provided 3 artificial cfDNA samples. We manufactured them by SensID in Germany, and each of those samples contained 18 nanograms per mil of cfDNA in a total volume of 3 mils of plasma per sample. We selected samples for specific BRCA1 or BRCA2 variants and provided them a range of different variant allele frequencies, so 20 to 50%. And those samples were validated independently by 2 different laboratories and by the manufacturer using droplet digital PCR. So one laboratory used an analysis using a custom hybridization-based NGS approach, and a second laboratory used a different NGS approach using capture automated with a Magnus system. Next slide, please. So looking at case 1, so obviously this is a prostate cancer setting. This individual had metastatic castration-resistant prostate cancer, previously been treated with hormone therapy, and was now showing signs of clinical progression. So a progression case. Tumor tissue testing had been attempted, but the results were inconclusive because the DNA itself was highly fragmented, and cfDNA analysis had been requested to determine the eligibility for treatment with PARP inhibitors. So it's a progression case after first-line hormone and chemotherapy treatment and insufficient tissue for a somatic test. So is there a pathogenic variant present in this individual ctDNA? Next slide, please. So in this case, there were no pathogenic variants detected in BRCA1, but there was a pathogenic variant deletion detected in BRCA2 using this reference sequence. And this sample had been manufactured with a 50% variant allele frequency. Looking at the validation data, so we were expecting to see 50% VAF, which had been measured by the manufacturer using digital droplet PCR. The data from the laboratories was reasonably consistent. So one laboratory reported 42% VAF, and the second validation laboratory reported 47% VAF. Looking at the breakdown of the results from the laboratories, about 95% of laboratories reported the correct genotype, so really good. And a further 5% of laboratories, just over, reported a critical error. And when you break down those incorrect results, they were all false positive results. So one laboratory reported a BRCA2 variant in addition to the expected variant, so an additional BRCA2 variant. One laboratory reported a BRCA1 variant, and another laboratory reported a different BRCA2 variant, in fact, two different BRCA2 variants. Next slide, please. Looking at the interpretation, there was one critical interpretation error, so 2% of the total number of reports, where the laboratory classified the variant according to germline somatic guidelines and stated that the variant is determined to be somatic, and therefore the patient should not receive PARP inhibitors if it was a VUS. So this was deemed by the assessors to be potentially clinically dangerous because the patient would have got the wrong prescriptive outcome. Two laboratories gave no indication of the pathogenicity of the variant detected, and a further 12, so 21% of the total, did not provide sufficient details of the variant classification system used. It's also quite possible that the pathogenic variant in BRCA2 could be germline in origin, and therefore we were expecting that laboratories would either refer the patient to clinical genetics or request a sample for germline analysis. So 18% of laboratories, so 10 laboratories didn't do this, and a further 4% received a deduction for a misleading comment as they strongly assumed that the variant was germline based on the variant allele frequency. Don't forget this is 50%. It's understandable why you might say that. And due to technical or biological reasons, obviously VAF is not a reliable indicator of the somatic or germline nature of a variant in cfDNA. So it's often used as a proxy, but it should be done very carefully as to whether that's really truly a somatic or germline variant. Several laboratories also received deductions for not providing sufficient details of methodology, limitations of the tests performed, and scope of their assays. Next slide, please. So case 2 was a gentleman with castration-resistant prostate cancer, again, that metastasized to his bones. He'd received taxane-based chemotherapy and hormone therapy, but was now progressing, was being considered for treatment with PARP inhibitors, and therefore cfDNA testing had been requested. Next slide, please. So in this case, there were again no pathogenic variant expected in BRCA1, but a pathogenic variant was expected in BRCA2. But this time, rather than 50%, we'd manufactured a 20% VAF. Looking at the validation data from the laboratories, one laboratory reported at 17% and the other one reported also at 17%. So pretty accurate between the two laboratories and very close to our expected 20%. Again, very similar to the results for case 1, just over 96% of all the tests done were correct, with a further just over 3.5% of laboratories making critical errors. And breaking down those errors into a bit more detail, again, false negative results, two false negative results, laboratories failing to report that BRCA2 variant in this sample, this time at 20% VAF. Next slide, please. There was 2% of total tests, critical errors, interpretation errors. Common deductions across the board were for not providing the details, so very similar, in fact, actually to the previous case. So not providing enough details on clinical referral to clinical genetics or request for a germline sample, information on pathogenicity of the sample, or the variant, should I say, detected, and evidence of the methodological approaches used by the laboratories. So all common problems that we see across the board, but obviously amplified in the context of a ctDNA sample, which is obviously quite challenging technically to actually get a good result on. Next slide, please. Case 3 was a gentleman, again, with castration-resistant metastatic prostate cancer, had received chemotherapy and hormone therapy. So again, very same as the first 2 cases, now progressing, being considered for PARP inhibitors, and ctDNA samples have been sent for testing. Next slide, please. So there were no critical genotyping errors or interpretation errors in this case. Just over 96% of laboratories got the correct result, and there were a further 3.5% of laboratories got a failed test result. So no result reported, but no critical genotyping or interpretation errors, which is fantastic to see. Next slide, please. Looking at the methodological approaches, again, similar sort of story. Again, very broad range of different tests used, 55 different approaches used across the 57 or so laboratories that took part or submitted results for this EQA. Next slide, please. Looking at the scoring, so the cases, the first 2 cases, which included a pathogenic variant, were pretty consistent across the board for both genotyping, interpretation, and clerical accuracy. And the analytical process for the third case, which was the cfDNA negative case, good testing, but the interpretation score, the genotyping score was high, the interpretation score was correspondingly lower, and that's really reflected in the omissions from the reports relating to the complexities of cfDNA testing, how you verify that the sample has no cfDNA in it, or ctDNA, should I say, and emissions of things like referral to clinical genetics, etc. All of those compound to bring down the score down from the 2 to closer to 1.3, 1.4, which indicates there's definitely more to be done in terms of how you report the results for these negative cases. Next slide, please. Looking at the performance trends, so there was about 20%, or just over 20% of laboratories didn't submit a result for the EQA scheme, which is pretty much similar to last year. In fact, more laboratories didn't record why they weren't submitting a result, which led to about 57 laboratories in total being assessed in the EQA when 70 odd had been registered for it. Looking at the error rates, although down from last year, they're still hovering about 3% for genotyping and just over 2% or just over 1% for the interpretation error. Again, it's too early days really to draw any strong conclusions from that. And obviously the variants we've included this year, we did vary the variant allele frequency. So it is good to see that the genotyping error rate has dropped, but it will take several more rounds of EQA before we can really see whether that's a true trend or whether that just reflects the clinical scenario we sent in this year's EQA. Looking at the poor performance data, well, this was the first year we'd actually provided the scheme based on ratified performance criteria, first 2 years with pilots. And so the poor performance rate, poor performing laboratories, is about 9%, which is about par for course for a new EQA scheme, which has just been sort of setting out to sort of establish performance metrics associated with a test strategy. What is good to see, though, converse to what Sandy reported in the somatic scheme, that all of those errors were related to one case only, and there were no instances, for example, of sample swaps between the different cases, or laboratories making repeated or multiple errors in the different cases provided. So that was a positive finding from that perspective. Next slide, please. So I'm now going to hand over to Sandy Deans, my co-chair, to give you a sort of overview of the shared learning from all 3 EQA schemes.
Great, thank you, Simon, very much. So as Simon says, I'm going to try and summarize it all together. So first of all, one of the key things to share with you is that these are currently data that's undergoing the appeals process, so we don't expect to be much change of the stats, but obviously there will be potential returning of marks or changes of comments imminent over the next couple of weeks, and you'll be notified of those from your EQA provider, and then the finalised EQA summary reports will be issued very shortly. So that's just something to bear in mind. So next slide, please. So some of the positives here, we're seeing a really improved number of laboratories that are complying with HGVS variant nomenclature, which is brilliant to see that standardization, and also help with the data submissions to international and local databases. That standardization is really important that way. Improvement of the use of reference sequences. We're seeing one being used per gene, and the main initiative being supported, which is exactly what EMQN and GenQA would like, and we support the main initiative. We're also seeing improvement in reporting format, so moving away from very, very long page reports, multiple page reports, to more concise 1 to 2 pages, fewer long, complicated multi-page reports, which means that you can find your result much, much easier, and you can minimize misinterpreting that report. Next slide, please. However, there's still some work to do. Variant classification, and this covers all of the EQAs that we've discussed today. So many laboratories are still using just a single source, predominantly ClinVar, for evidence. But ACMG and the other guidelines, such as the AMP-ASCO-CAP guidelines for somatic validation, guidelines and Enigma, etc., are also available in other resources, and it's good practice to use multiple sources to be able to ensure you have the most information available for that variant classification. We're still seeing, and in particular, quite a few labs in the somatic EQA, laboratories reporting the presence of non-pathogenic variants, in particular benign or likely benign, so that's your class 1 and 2. We really would not like them on a report. They can be misinterpreted and confuse the reader of the report, that they might infer that is actually a pathogenic or a disease-causing variant. So we would much rather they were not stated on the report. Obviously, they will be kept and held on record within the laboratory, but not to report them to the clinical team. With regards to the interpretation of the result, we would like the clinical question being asked, so the actual tailored interpretation to the scenario that is provided. So we're seeing many labs still not having a statement about the patient's likelihood of benefiting from a targeted therapy in the interpretation, bearing in mind that sometimes local reporting or the reporting on the providing clinical interpretation may not be within the scope or the remit of the service you provide, but you can upload supporting information to the EQAs to actually convey this information to the assessors. Also, when clinically relevant variants are not found in a germline sample, then it's really important to make sure that you recommend testing of the tumour, because there may still be a somatic pathogenic variant present in the tumour that is not picked up on the germline test. So it's not just about the referring patients to clinical genetics when you've got a variant in the tumour, but it's also on the flip side that it may be present in the tumour only and not in the germline. Next slide, please. For BRCA1 or BRCA2 pathogenic variants detected in the tumour, this is the flip side, you have to remember that it may be germline in origin. So you want to refer to clinical genetics for further investigation, or for genetic counselling, or whatever is best practice or local practice in your own service. It's important to comment within the report that this has a potential impact on the family of the patient. So it's not just about the individual. You need to be aware that it is potentially could impact the wider family. Also, we have some laboratories over-interpreting when no pathogenic variant has been detected, so no actionable variants detected result. So advising that the absence of a variant indicated that the patient would be unlikely to respond to targeted therapy. So that is an appropriate interpretation of the result. So we would really advise more caution, as the circulating free DNA analysis are known to have reduced sensitivity for detecting variants, so you need to be aware of the limitations of the test that you are performing. So in the event of no actionable variants being detected, a repeat sample should be requested, and probably good practice to have as well, a clear statement regarding the reduced sensitivity of plasma testing compared to testing a somatic tissue. And the risk of no circulating tumour DNA being present in the sample is a really high, needs to be definitely highlighted to the reader of the report. Next slide, please. Two key messages that we really have to flag to participants is many laboratories did not demonstrate the full understanding of the limitations of their cfDNA testing, and Simon's gone through this in quite a lot of detail. So we know that the technical limitations in terms of analytical sensitivity and limit of detection are there, but also biological considerations around the levels of circulating free DNA in the tested samples is something that you need to take into account, particularly if no pathogenic variant is detected. And also a big take-home message, particularly from the germline and the somatic EQAs this round, is testing for copy number variants, including large genomic rearrangement, should be considered as essential. And we know that there's published data out there saying that about 15% of inherited BRCA1 and BRCA2 pathogenic variants are large genomic rearrangements. Therefore, to really have a truly clinical utility to your testing, you should include these into your best practice and pathway. Next slide, please. So some key dates for the EQAs running in this calendar year. So our 3 EQAs will be being distributed. The samples will be shipped out in mid-September this year. Submission of results in the same time frame will be mid-November, with the final published results coming out post assessment, and appeals will be April 2026. So the exact dates are still to be finalised, and you'll be informed of those from your EQA provider. Next slide, please. So thank you very much for listening. Next slide, please. I would encourage you to put your questions in the Q&A function here. So Simon and I, we've got a little bit of time left that we can answer any queries or clarify some points. So please do that. Simon, I think we have one question at the moment. So where can we get the performance evaluation feedback? So I mentioned that we were just coming through the appeals process at the moment. Where do participants access their data?
Thanks, Sandy. So, yep, if you're not familiar with the EQA process, then what we do 2 parts to your analysis effectively. So one of them is the individual tailored feedback that's bespoke to your laboratory. So we give you detailed feedback on how your laboratory performed in the context of the EQA. And that's in something we call the individual laboratory report, which basically gives you a full breakdown on the performance, your performance of the laboratory and how you did, and any questions associated with that and any deductions associated with your performance in the EQA. But I think more importantly, I think is laboratories really want to know how well they did compared to their peers. And that data is summarized in the summary scheme report, which gives you an overview of how everybody did in the EQA scheme, what the common problems were associated with it, what people did well, what people didn't do so well, how they approached the testing, data on performance metrics in terms of how the different tests actually performed in the real world. So that's those two items, the individual laboratory report and the summary report, are the key outcomes of performance measurements of the EQA. Thoroughly involved, we get into a bit more detail, particularly in the summary report. It's a very detailed report, lots of educational content there. Remember, what we're trying to do is help educate the community on how best to approach these testing strategies.
Thanks, Simon. We've got some questions coming in here. I'm going to ask you one about ctDNA. So, and we don't often get asked this about being more challenging, but will there be more challenging ctDNA testing? So some of these cancers barely shed detectable ctDNA, like as we know, lung is a low shedder, but 20% variant of allelic frequency is very high.
It is, and we know that this is the limitations of the samples we provide. But the reality is, it's really, really difficult to make materials for BRCA testing in a ctDNA format. So although you can buy reference materials off the shelf for defined variants like EGFR at very low variant allele frequencies, validated using whatever approaches, droplet digital PCR, for example, when you're trying to make a reference material for something like BRCA1 or BRCA2, where they could, you're not looking at defined private mutations, you are looking at potentially mutations across the entire large gene. Those materials just don't exist in the reference material providers, and so we acknowledge there is a compromise we have to make when we make these materials. That means that the samples we use as our background, or if you like, our background cell line, haven't been engineered. They are endogenous variants in those genes. And therefore, when you manufacture the samples, it's not possible with the same levels of accuracy to mix the background cell line with the sample with the variant and get samples down to low variant allele frequencies that would work reliably in the clinical test setting. So we are slightly constrained by what we can do with respect to making the materials. And this year, actually, 20% sample was more challenging than previously provided. But we are aware of those scenarios and looking at alternatives that may allow us to test down to lower frequencies. But the question was very relevant and something we are aware of and trying to improve in future rounds.
In fact, that's the approach that we use for our lung cancer and our other ctDNA testing EQAs, isn't it? It's just the fact that the BRCA genes are so large that's the true challenge.
Yeah, it's really challenging making these. So, I mean, it's also really challenging for you as the laboratories doing the testing, as evidenced by the results. So it works both ways. Yeah. Sandy, I've got a question for you. So this question says, have you looked at the method which method's best used for detecting CNVs in BRCA?
Right. So I think CNVs have traditionally in BRCA been tested using MLPA analysis, but I think with the changes in bioinformatics, many people are now calling CNVs off their exomes or their targeted panels. So obviously NGS is probably the best way to go forward. However, I don't think we could say which method in particular was best, because everyone's bioinformatics analysis is ever so slightly different. So I think you really are dependent in your bioinformatics pipeline to the accuracy of your CNVs. I mean, obviously you need a sort of a SNP backbone present so you can call that copy number variation accurately, but I would definitely say NGS, but speak nicely to your bioinformaticians or have in-house expertise if at all possible, because that will really make the difference to whether or not you pick them up. And you can see from particularly the somatic education case that there was a really high number of false negative results. So I would definitely say tweak the bioinformatics. It may not be the wet work that is actually the issue there.
But is it also true to say, though, certainly in the germline setting, there are other strategies that people use routinely in the germline setting? Yeah.
I think the somatic is more challenging because of your variant allele frequency.
And what we obviously expect to see that being very challenging for laboratories, which is why we made that case educational listing. Absolutely. Two more questions.
OGM one, I can do that. That's open now. So the GenQ OGM EQA for 2024 is still open and nearly about to close, and registration's open for the 2025 EQA. So do go to our website or drop me an email or info@genqa.org and we can get some information to you about registering for that one. How do you determine HGVS breakpoints for exon deletions on targeted panels? Somatic. Do you want to take that one, or will I take that?
I'm going to give that one to you because that's not my area of expertise.
We can't, basically. I think Simon and I both, across all of the EQAs and the disease-specific EQAs that we run, try and avoid recommending HGVS for CNV reporting. You don't know your exact breakpoints depending, and it very much depends on the methodology that you're using. If you're using especially targeted panels, you're only going to find the breakpoints that your targets can detect, not actually the true breakpoints. So we tend to then say, try and report on exons rather than using actual genomic breakpoints. So I think that would be the way forward. But as we've seen with this EQA run, it's really important that your exon numbering matches your gene reference sequence, because they can mean different things. And if in time, if you're going on to do a family cascade test, for example, to other members of the family, or that's performed by another lab, they might be looking in the different part of the genome or the gene that you think you're looking, and they may get false negative results. So avoid HGVS, I would say, but accurate exon numbering is key.
But that latter point is really relevant in the context of BRCA testing as well, Sandy, isn't it? Yeah. Because the BRCA testing is, certainly in the germline context, has been around for a very, very long time. And so the use of legacy nomenclatures associated with that is traditionally fixed within many laboratories. So it's not just about stating, it's also about understanding the limitations of the legacy numbering you're using, or at least acknowledging that you've used a particular nomenclature. Because that transferability between stating what the variant is between different reports is dependent on actually knowing what you've referenced it against in the first place.
And databases, you can go and pull off some clinical interpretation or your pathogenicity classification, and if it's not the same deletion or duplication, then it's important that we all speak the same language. Yeah.
We've got one last question here, Sandy, which is entertaining me, I think, is the way I describe it, because obviously we've demonstrated from the EQA the complexities of just doing CMV analysis, but then we're also question is will we include detection of loss of heterozygosity in our EQAs moving forward? Very interesting question, and I think given what we've demonstrated so far, probably not in the near future, not just yet anyway.
But we have got it in other EQAs, so our MSI and our colorectal cancers with MLH, etc. So it is
included in some of
those.
Yeah, absolutely.
So if it's principles of your assay detecting LOH, then yes, it's covered, but not in these particular EQA ones. Where I think with the error rates that we're seeing with the CNVs, I think it's one to be considered in the future.
Yeah, and just to, I mean, I don't think Sandy and I really covered. We perhaps should have covered this in our presentation, but what we will, in future, we would like to include in the webinar itself is just the evidence of improvement in performance over time. And so we do have quite good data from this EQA scheme to show that the number of successive participations in the EQA does improve your chance of good performance in the EQA. So performance improves dependent on how many times you participated. So labs that participate regularly, routinely, whatever you like to call it, but every year is what we would classify that as, definitely perform better than laboratories that perform either sporadically or have only participated once or twice in the past. And I think we've perhaps not brought that through in the real data of the analysis of the schemes, but certainly in future we'll try to include that, because I think it's really strong and strong evidence now to show, after 9 years of these EQAs, that the data definitely shows you need to be doing it regularly, routinely, because you can't cover every scenario in just 1 year or isolated sporadic years of participation.
Yeah, absolutely. I would echo that. So Simon, I think we've answered all our questions. Can we go into the last slide, please? That's just a QR code for you to give some feedback if you would like to. We'd appreciate that, just to find out what areas of the presentations you found in particular interesting, so we can deliver more of that for you in the future. And just a huge thank you both to EMQN's team and GenQA's team, who it's Simon and I just do these webinars. They actually do a huge amount of work and are a clinical input as well. So thank you very much, and to also our EQA assessors, who again contribute tremendously to the delivery of these EQAs. So, and also to MSD and AstraZeneca for their continued educational support for delivering these services to the laboratories. And of course you, Simon, for joining us today as well and doing a great double act. So thank you from me.
Thank you, Sandy. And one final thing, thank you to you, the participants, for listening and for participating in the EQA as well. They wouldn't exist without you actually contributing to it. So thank you as well.
Great. Thank you very much. Goodbye, everyone.
Bye, everybody. Have a good afternoon.